Assalamualaikum and salam sejahtera. We are from Group 21 and today our group will explain about corrosion of matter. First, what is corrosion? Corrosion is slow damage or deterioration of matter caused by chemical or electrochemical reaction with the surrounding, such as water, oxygen, acid, or salts. It is important to study corrosion because it leads to major economic loss. Machine structures and pipelines need frequent repair or replacement. Corrosion can also cause serious safety risks, for example, when bridge, vehicle, or industrial equipment fail. Besides that, corrosion also affects the environment, especially when leaking pipeline release oil gas or chemical into soil and water. Corrosion actually works like a small electrochemical cell on the metal surface. At the anode, ion undergo oxidation forming Fe2 plus ion and release electrons. These electrons flow to another part of the metal surface, the cathode, where oxygen is reduced in the presence of water. The Fe2 plus ion produced then react with oxygen to form brights, which the brown flaky substance we usually see on the crowd ion. In summary, corrosion involves oxidation at anode, reduction at cathode, and represent of an electrolyte like water, which completes the electrochemical process.
Good day, everyone. So today I'll be presenting on the fundamental electrochemical principle that involve in corrosion. Corrosion is not simply the rusting of metal, it is actually an electrochemical process that involves electron transfer reaction. So whenever a metal corrodes, its surface separates into two distinct regions, which is anodic and cathodic areas. Electron flow between this region and ions move through the surrounding environment, such as water. So this combination of oxidation and reduction reaction is what drives the corrosion process. Okay, as for the corrosion as an electrochemical cell, so corrosion can be understood as a type of electrochemical cells that occur naturally on a metal surface. So even on a single piece of metal, different areas will behave differently due to its surface imperfections, or maybe it has any impurities or oxygen differences. The anodic region, the metal will undergo oxidation and release electron, while in the cathodic region, a reduction will take place where a species in the environment like oxygen or hydrogen ion will accept those electrons. So these two half reaction will happen simultaneously to form a complete electrochemical cell that continuously drive corrosions. So let's break down the reaction happening at each site. So at the anode, the fundamental reaction is oxidation. So metal atom will lose its electron and dissolve it into solution as metal ion. While at the cathode, the electron will release from the anode must be consumed. In neutral or passive environment, oxygen is typically reduced to hydroxide ion. In acidic environment, hydrogen ion will gain electron to form hydrogen gas. So these two half reaction work together and sustain the process. Okay, now electron and ion flow. So corrosion cannot happen without the movement of electron and ion. So electron flow through the metal itself from the anodic area to the cathodic area, and at the same time, ion move through the electrolyte such as water or moisture in the air. Metal ion that form at the anode migrate away into the electrolyte, while anions such as hydroxide or chloride will balance the charge. So this movement is essential because corrosion requires both electron and ionic pathway. So if either path is blocked, corrosion will slow down or stop. Electric potential. So electric potential help us predict which metals are more likely to corrode. Every metal has its standard electric potential, or we mostly known as inert value. So as we know, metals with more negative inert values will oxidize easily. So when it oxidizes easily, corrode will happen more readily, while metals with more positive inert values are more stable and less likely to corrode. So when two different metals are in electrical contract, the one with the more negative potential becomes the anode and will corrode faster. So this is what we call as galvanic corrosion, and we can commonly see it in pipelines or construction structures. And for the last is the Nernst equations. So this equation will allow us to calculate the actual electric potential under specific condition, especially when concentration are not at standard values. This equation shows that as the concentration of metal ions increase near the surface, the potential shift and corrosions slow down. But if ions are constantly washed away by moving water, the concentration stays low, making corrosion continue rapidly. So this is why metal in coastal or flowing water environment corrodes faster.
So next we will discuss about types of corrosion. So the first one is uniform corrosion. This is the most common and also the least dangerous types of corrosion. It will form a uniform layer across metal surface that is caused by the absence of a protective coating and also exposed to corrosive agent such as moist air, acid, seawater and also humid condition. And this type of corrosion actually occurs through oxide forming chemical and also electrochemical reaction. And we usually see this type of corrosion in lead, iron, steel, zinc and aluminum. So next is galvanic corrosion. For galvanic corrosion, it occurs when an electrolyte is present and two dissimilar metals come into physical or electrical contact. So as we can see in the picture, right, the less noble, which is the active metal, and the anode part will corrode faster. However, the another part, which is the right side, as you can see here, the more noble, the cathode part is protected. So this type of corrosion actually very common in a marine setting where the salt water will become the electrolyte. And the third one is stress corrosion. It occurs when we apply a tensile stress to a metal in a corrosive environment. So first it will just begin as a tiny surface cracks that will eventually grow and also lead to structural failure. For example, copper alloy in ammonia and also stainless steel in a chloride condition. And the last one is pitting corrosion. So this is one of the most dangerous type of corrosion because it is unpredictable and also it's difficult actually to detect. So it will form rust pits or holes on the metal surface that descend into deep cavities that caused by flaws in protective coating, surface damage or outside layer breakdown. And it usually occurs in aluminum, nickel alloy and also steel.
Corrosion occurs through an electrochemical mechanism. On a metal surface, there are naturally formed anodic and cathodic regions. At the anode, iron atoms lose electrons and form ferrum 2+ ions, meaning oxidation occurs. The released electrons travel through the metal to the cathodic region. At the cathode, oxygen from the air dissolves in water and is reduced to hydroxide ions. These hydroxide ions then combine with ferrum 2+ to form iron hydroxide, which is later oxidized to hydrated iron 3 oxide known as rust. This process requires moisture, oxygen, and an electrolyte such as salt. Electron flow from the anode to the cathode and ion movement in the electrolyte complete the corrosion circuit. As a result, the metal surface gradually deteriorates. The specific value of X can vary depending on the conditions under which the rust forms, but it is often represented as a small number, sometimes even as a specific value like 2.
So next, we will talk about the factors that affecting corrosion. So the first factor is environmental condition. So condition like humidity, it will actually increase the moisture layer on metal surface, which this will help to form electrolyte films and will make electrochemical reactions becomes more easier. Other than that, salinity, especially in marine setting, it will add chloride ions that will break down protective oxide layer. So this will increase the corrosion. Other than that, higher temperature also will increase reaction rates and lead to faster corrosion. Second one is presence of electrolyte. So electrolytes, it will allow ions to move and this will form a tiny corrosion cells on the metal surfaces. Water and dissolved salt also will increase conductivity. So this will make the electrons and ions to flow more easily and speed up the metal dissolution. Consequently, higher ion concentration will make the electrolyte become more conductive and result in faster and more aggressive corrosion. And the last point is material properties. The chemical composition and also allowing elements actually determine a material's natural corrosion resistance. So elements like chromium and also nickel actually enhance protective outside layer, while others just reduce stability. Other than that, microstructural features such as grain sizes and also phases, it will also affect on how evenly and quickly corrosion will occur. So overall, materials with stable electrochemical behavior will perform better in a corrosive environments.
Today I will give a brief overview of how corrosion affects several major industries and why understanding it is so important. First, pipeline corrosion. Pipelines are buried or submerged, making corrosion a major safety concern. Moisture, soil, and contaminants like carbon dioxide, hydrogen sulfide, and chlorides all attack the metal. Over time, this can weaken pipeline and lead to costly failures. Next is marine corrosion. Saltwater environments greatly accelerate corrosion. Ships use sacrificial anodes, usually zinc or aluminum blocks, to protect their hulls. These anodes corrode instead of the ship, extending its service life. Next is infrastructure. Reinforced concrete structures such as bridges also face corrosion. Moisture seeps in, cracks the concrete, and reaches the steel rebar inside. As the steel corrodes, it expands, causing further cracking and structural weakening. Next is automotive. Car bodies are often galvanized or painted to prevent rust. Road salt, moisture, and oxygen create highly corrosive conditions, especially in winters. Modern cars also face corrosion on components like brake lines and steel fuel tanks. Next is aerospace. Aircraft rely on high-strength aluminum alloys and stainless steels because of the extreme conditions they experience. Fuel tanks and hydraulic lines can suffer from pitting and stress corrosion cracking. That's why the aerospace industry uses protective coatings and strict inspection routines. Next is energy and utilities. Power plants and cooling towers operate in harsh conditions. Boilers, condensers, and water handling equipment often experience internal corrosion and stress cracking, which can lead to expensive downtime if not properly managed. These examples show that corrosion is a widespread challenge across many industries. By understanding its causes and using protective strategies, we can prevent failures, reduce costs, and ensure safety.
Next, I will be presenting about corrosion detection and monitoring. These methods are essential because they help industry preserve material health, prevent failures, and reduce maintenance costs in systems such as pipelines, ships, aircraft, and industrial structures. First, we have the corrosion coupon method. A corrosion coupon is simply a small metal piece inserted into a system. After a certain period, it's removed and analyzed to determine the amount of corrosion. It's a straightforward but effective way to monitor corrosion over time. Next is electrical resistance monitoring. This technique measures how the electrical resistance of a sensing element changes as it corrodes. Since metal loss affects resistance, this method provides continuous online monitoring. Next one is acoustic emission monitoring that uses sensors to detect elastic waves produced by corrosion activity. When corrosion damage occurs, it generates straight waves, and this system listens for those signals to identify problem early. And the next one, ultrasonic testing that appears in two parts. The first one uses high-frequency sound wave to measure material thickness, helping detect corrosion from one side of the structure. And the second one, as shown, is magnetic flux leakage, which uses a magnetic field to identify corrosion, pitting, or wall loss, especially in pipelines and storage tanks. And finally, infrared thermography detects the temperature differences on a surface. This variation can indicate subsurface corrosion, making it useful for fast non-contact inspection. In summary, this method work together to provide early detection, continuous monitoring, and better prevention of corrosion-related failures.
Preventing corrosion typically involves multiple strategies. Coatings and paints create a physical barrier between metals and water or oxygen. For example, galvanizing steel with zinc provides superficial protection. The zinc corrodes first if the coating is breached multiple times. Cathodic protection is widely used in power line and marine structures. Electrical current is applied or superficial anode is attached, so that protected metals remain acidic. Material choice matters to using stainless steel or aluminum greatly reduce corrosion. In liquid systems, corrosion inhibitors can be injected into liquid to chemically slow down material oxidation. Together, those methods form a comprehensive corrosion protection system.
So for the application of electrochemistry in corrosion control, the first is galvanic cathode protection. This is a simple but brilliant method used for smaller structures like pipeline and sheet parts. We attach a more reactive artificial anode like zinc or magnesium. This anode corrodes instead of the structure, artificially protecting it. The second method is increased current cathode protection. For larger accessories like bridge or storage tanks, we should use an external DC power source to force protective current onto the structure, making it a cathode and stopping the corrosion reaction entirely. To monitor this system, we should use an LVR meter. This device applies a small voltage to a metal probe and measures the current response. This polarization resistance gives us an instant readout or corrosion rate, allowing for quick adjustment. Next, a corrosion inhibitor is a chemical substance that protect the metal surface. Its work is one or two way. First, through absorption, where organic molecules form a thin protective film by sticking to the metal surface. Or second, through oxidation, where an organic compound helps form a passive protective oxide layer that acts as a shield. This concept of a precise layer is taken a step further with anode protection, unlike cathode protection. This method makes the metal structure the anode of the cells. By applying a carefully controlled current, we force the metal into a stable, passive state where it forms its own highly protective oxide layer, effectively putting it into a state of suspend animation against corrosion. Lastly, for the future direction, first we have smart coating. Imagine a coating that can heal its own structure. It's self-healing technology using embedded microcapsules. Furthermore, nanotechnology with material like graphene is creating ultra-strong barriers that can release inhibitors on demand. Second, advanced monitoring is key. By using AI and sensor, we can now predict corrosion before it happens. This data can feed into a digital twin, a research mode, or an assets, allowing us to test and optimize protection strategy in real time, safely and cheaply. Finally, the shift is toward green solution. We are replacing toxic inhibitor with eco-friendly alternative derived from plant X-ray and developing new bio-based coating and alloy to minimize environmental impact. This future is about proactive, intelligent, and sustainable protection.